A monumental dam in the heart of Africa is failing. It is holding back the world's largest man-made reservoir, and it is threatening to unleash a catastrophic flood upon 3.5 million people. The official engineering reports are terrifying. This single structure impounds over 180 billion cubic meters of water, a volume 4 times greater than Lake Mead behind the Hoover Dam, and for decades, it has been compromised by two separate relentless forces of decay. One is a slow, chemical cancer eating the dam from the inside out. The other is an invisible abyss being carved out of the bedrock directly beneath its foundations. This isn't a distant theoretical problem. The warnings have been issued. The countdown had begun. What do you think is the most terrifying part of a potential dam failure? The initial wave or the lasting flood? Let us know in the comments. The documents that expose this crisis are staggering, and we spend hundreds of hours digging through technical reports and expert opinions to bring you the full story. A shocking number of people watch these deep dives to the very end, and just forget to subscribe. If this kind of reporting is important to you, please take 1 single second and hit that subscribe button. It's the one action that ensures we can continue to make these documentaries. You will be glad you did. Now, let's begin. The structure is the Kariba Dam, a 128-meter-tall curving wall of concrete stretched across the Zambezi River, forming the border between Zambia and Zimbabwe. It was opened by Queen Elizabeth, the Queen Mother, in 1960, a colossal symbol of post-war engineering ambition, designed to harness the power of Africa's fourth longest river and provide electricity for 2 growing nations. For 60 years, it has done just that. But behind the facade of power and progress, a dual crisis has been escalating in silence. Here is the detail that tells the real story. Engineers are fighting a war on 2 fronts. The first is underwater. For 6 decades, the immense power of the water released from the dam's floodgates has been acting like a hydraulic chisel. It has hammered away at the soft gneiss rock at the dam's base, blasting out a crater 80 to 90 meters deep. This is not just a hole. It is a gorge, an underwater canyon that has been creeping steadily back toward the dam's foundations, threatening to undercut the entire structure and cause it to fail. And that is only the first battle. The second is happening inside the dam itself. The very concrete used to build this monolith is betraying it. A slow chemical process called Alkali-Aggregate reaction, or AAR, is causing the concrete to swell. It's a kind of structural cancer. A gel forms inside the mix, absorbs moisture, and expands. This expansion exerts immense, irresistible pressure on the dam's components, deforming the structure. Crucially, it is squeezing and jamming the 6 massive spillway gates, the very mechanisms needed to release water safely during an extreme flood. The dam is losing its ability to save itself. This is how it happened. Construction on the Kariba Dam began in 1955. It was an audacious project undertaken by an Italian consortium, Impressit, in an era of boundless technological optimism. The goal was to tame the wild Zambezi and create a powerhouse for the Federation of Rhodesia and Nyasaland. But the river did not yield easily. The local Tonga people, who had lived along the river for centuries, believed in a river god, Nyami Nyami, with the head of a fish and the body of a serpent. Their legends held that the dam was an affront, a wall built to separate Nyami Nyami from his wife downstream. And twice during construction, the river seemed to prove the legend true. In 1957, and again in 1958, biblical floods far exceeding all engineering predictions descended on the worksite. The waters completely overtopped the partially built coffer dam, washing away equipment and killing several workers. To many locals, it was the fury of a separated god. To the engineers, it was a brutal reminder of the Zambezi's untamable power. Despite the setbacks, the dam was completed in 1959. As the gates closed, the waters began to rise, slowly drowning a vast landscape of forests and hills. This created Lake Kariba, and it also triggered one of the largest animal rescue missions in history. Codenamed Operation Noah, the effort took 5 years, from 1958 to 1963, saving thousands of animals stranded on newly formed islands as the water crept higher. Elephants, rhinos, lions, zebras, and countless smaller creatures were tracked, tranquilized, and relocated to the mainland. It was a dramatic, inspiring tale of man correcting for his own environmental disruption. But the very force that necessitated Operation Noah, the immense static weight of 180 billion tons of water, was also setting the stage for future disaster. That weight pressing down on the Earth's crust has been proven to trigger reservoir-induced seismicity, causing a swarm of small and moderate earthquakes in the region for decades. The dam was not just holding back a river, it was altering the very geology of the continent. For years, the dam operated. It generated power, it sustained industry, and lit up cities. But the seeds of its decay were sown in its initial design. The engineers who planned the spillway expected the powerful jets of water to scour out a stable plunge pool at the base, and then stop. They miscalculated the resilience of the rock. The gneiss was softer than anticipated. And so, with every major release of water, the hole just kept getting bigger. Year after year, decade after decade, the erosion continued unchecked, like a cavity eating away at the root of a tooth. By the early 2010s, surveys returned shocking results. The hole was not just deep, it was regressive. It was actively cutting its way back toward the dam wall itself. An expert panel convened by the World Bank issued a chilling warning. Without intervention, a major flood event requiring prolonged spilling could cause the erosion to reach the dam's foundations, leading to a structural failure in a matter of a few years. It's a terrifying thought, to imagine a dam eating itself from below. If you've just learned something new or had a whoa moment about the science behind this, hit the comments and let me know. I do read all of them. And here is what made it so much worse. While the foundation was being eaten away from below, the concrete was swelling from within. The Alkali-Aggregate reaction wasn't a fast process. It was a slow, patient crisis unfolding over half a century. The aggregate, the crushed rock mixed into the cement, was reacting with the alkaline paste around it. This chemical process is irreversible, and the consequences are catastrophic for a structure that relies on precise geometry. As the concrete walls of the spillway guide slots expanded, they began to constrict the giant steel gates. The gates, each the size of a small house, need to move freely to manage the lake level. If they jam shut during a monsoon season, the lake could rise uncontrollably, overtopping the dam crest and triggering a complete failure. If they jam open, they could drain the reservoir, crippling the power supply for 2 countries and devastating the lake's ecosystem. The dam was becoming a trap, with its own safety features turning into liabilities. In 2014, the Zambezi River Authority, the binational body that manages the dam, made a stunningly blunt public statement. "We are told by the experts," they said, "that if nothing is done, the dam will collapse." Doing nothing was not an option. The true horror of a Kariba Dam failure is not just the loss of the dam itself, it is the domino effect. The failure would not be a single event. It would be the start of a chain reaction of destruction that would cascade through 3 countries. A collapse would release an inland ocean. A wall of water, a wave of unimaginable destructive force, would surge down the Zambezi River Valley. Projections show this wave would travel with terrifying speed. Within 8 hours, it would reach the border of Mozambique. But its primary target would be the next major obstacle in its path, the Cahora Bassa Dam. Cahora Bassa is the second largest dam on the Zambezi, another titan of concrete and steel located 500 kilometers downstream in Mozambique. It is a critical piece of infrastructure, providing most of Mozambique's electricity and exporting power to South Africa. It is a massive structure in its own right. But it was never ever designed to withstand the collapse of Kariba. The flood wave would arrive at Cahora Bassa in just 25 hours. It would hit not as a flood, but as a solid wall of energy, overwhelming the dam's spillway capacity and almost certainly triggering a second catastrophic failure. If this is the kind of critical global story that you think people need to know about, please share it. Send this video to just one person in your family or a friend who needs to see it. And if you do, hit that like button as a signal to us. It helps more than you know. The failure of Cahora Bassa would compound the disaster on a scale that is difficult to comprehend. 2 of southern Africa's largest dams would be gone. The combined volume of water from both reservoirs would rush toward the Indian Ocean, inundating a vast, heavily populated area of central Mozambique. The Zambezi Delta, a fragile and fertile ecosystem that supports hundreds of thousands of farmers and fishermen, would be annihilated. From the moment of Kariba's collapse, it would take just 97 hours, 4 days, for the flood wave to complete its journey of destruction to the sea. The total population living in the path of this deluge is estimated at 3.5 million people across Zambia, Zimbabwe, Mozambique, and even Malawi, which would be affected by flood backwash up the Shire River. It would be a humanitarian crisis of biblical proportions. Power grids would fail. Infrastructure, roads, bridges, hospitals would be erased. and millions of lives would be at immediate risk. Here is what was happening behind the scenes. Faced with the stark reality of imminent failure, the governments of Zambia and Zimbabwe, with the Zambezi River Authority, launched an unprecedented appeal for international help. The World Bank, the African Development Bank, and the European Union responded. The result was the Kariba Dam Rehabilitation Project, or KDRP, a $294 million emergency intervention to pull the dam back from the brink. It was a race against time, a monumental feat of engineering designed to fight the two-front war. The first priority was the plunge pool. The mission: to stop the erosion and stabilize the foundation. The contractor, a French firm named Beck, was tasked with reshaping the bottom of the riverbed while the dam continued to operate above. They had to build a temporary cofferdam on the floor of the plunge pool itself, in turbulent water, to create a dry work area. Then came the most dangerous part: blasting and removing 300,000 cubic meters of weak and fractured rock from the crater. It was like performing surgery at the bottom of a waterfall. Every blast had to be precisely calculated to remove the unsafe rock without creating new instabilities or damaging the dam's foundation just meters away. For several years, crews worked in this high-risk environment. The project was a modern marvel of engineering, using remote-operated vehicles and advanced modeling to reshape the abyss. In May of 2023, the Zambezi River Authority announced a major victory. The reshaping of the plunge pool was complete. A new stepped profile had been created, designed to safely dissipate the energy of the water and put an end to the destructive scouring. The first battle had been won. But the war was not over. Attention then shifted to the second, more insidious threat: the swelling concrete and the jammed spillway gates. This phase of the project is happening right now. It is arguably even more complex. Engineers cannot simply replace the concrete. The AAR is in the body of the dam itself. Instead, they have to perform a kind of bypass surgery. The project involves refurbishing all 6 of the massive spillway gates and, critically, retrofitting the structure that houses them. A new gantry crane and associated equipment are being installed on the dam's crest. This machinery will allow operators to manage the gates despite the distortion caused by the AAR. It involves replacing corroded components, installing new guide systems, and ensuring that when the next great flood comes, the dam's operators will have the ability to release water on their own terms, not on the terms dictated by a failing structure. This work is ongoing. It is a painstaking, high-stakes process happening 400 feet above the Zambezi, with 180 billion cubic meters of water pressing against the wall. The project is not scheduled for full completion until 2025. We're about to get into the fine details of the spillway gate replacement, the most delicate part of this entire rescue mission. If you're finding this story as gripping and important as we do, please consider subscribing. I know. It might be the second time I'm asking, but our data shows that a huge portion of our audience are regulars who just haven't hit the button. That click is the actual lifeblood of this channel. It takes 1 second, and it makes all the difference. So, for the next year, the dam remains in a state of heightened vulnerability. The foundation is now secure, but the release mechanism is not. The greatest risk has always been the convergence of events, a major once-in-a-century flood event occurring before the repairs are complete. If the Zambezi Basin receives unprecedented rainfall, forcing the lake to rise faster than the compromised gates can handle, the dam would still face an overtopping scenario. Every storm cloud that gathers over the region is watched with anxiety. Every meteorological forecast is a reminder that the race is not just against structural decay, but against the clock and the climate. Let's dissect the spillway project further, because its complexity is astounding. The 6 floodgates are located in the upper portion of the dam wall. Water from the reservoir must pass through an intake structure before reaching the gates. The problem with AAR is that it's not just squeezing the gates themselves, it's deforming the entire concrete block around them, including the guide slots for the stop beams. Stop beams are essentially massive steel logs that are lowered into slots upstream of the main gate to seal off the opening, allowing the gate itself to be dewatered and safely worked on. But if the concrete guide slots have swollen and narrowed, you can't get the stop beams in. And if you can't get the stop beams in, you can't safely repair the main gate. It's a structural catch-22. The engineering solution had to be incredibly creative. A key part of the current phase involves meticulously remachining the distorted concrete of these very guide slots. Imagine trying to shave a few millimeters of concrete off the inside of a submerged 400-foot tall structure, with tolerances so fine that any error could compromise the seal. It requires custom-built equipment and a level of precision that is almost unheard of in a field environment of this scale. This isn't just a replacement job. It's a reinvention of a critical part of the dam's anatomy, performed while the patient is awake. The new emergency gantry crane being installed is another piece of this puzzle. The original gantry might not have the power or the precise control needed to lift and lower gates that are binding in their slots. The new crane is a more powerful, more intelligent system designed to overcome the resistance created by the AR swelling, giving operators a mechanical advantage against the dam's own self-destructive pressure. This entire process is a vivid illustration of the long tail of infrastructure. Decisions made in the 1950s, using the best knowledge and materials available at the time, are now creating a 21st century crisis. The choice of aggregate for the concrete 60 years ago is now holding the fate of millions of people in the balance. It raises a profound question about all megaprojects. How do you plan for problems that may not manifest for 2 generations? The engineers of the 1950s were not negligent. They were operating at the limits of their material science. But the dam has outlived the certainty of its own design. It has become a living laboratory for the study of concrete aging, geological response, and long-term risk management. And the completion of the plunge pool works gives us a tangible sense of what is at stake. Upon finishing that phase, Munirazi Munodawafa, the CEO of the Zambezi River Authority, announced it was a significant milestone for a project of this magnitude and complexity. His words, while professional, barely conceal the immense relief. They had successfully disarmed one of the 2 ticking time bombs. But everyone involved knows the second one is still counting down. Until the spillway refurbishment is 100% complete and tested under load, the shadow of risk remains. It's a project where 99% completion is still a failing grade. Everything has to work. Okay, last time, I promise. Probably. If you're still here, this deep into the story, and you still haven't subscribed, what are you waiting for? An engraved invitation delivered by a rescued rhino from Operation Noah? Hit the button. Join the investigation. Your future self who loves these deep dives will thank you. Let's bring this back to the human scale. The dam is not just a piece of concrete. The crest of the wall itself is a road, a physical border crossing connecting Zambia and Zimbabwe. It is a symbol of shared history and shared destiny. The 2 nations co-own the dam and share its power, and now they share its monumental risk. The 2 main power stations, one on the north bank in Zambia and one on the south bank in Zimbabwe,